Now I am taking the topic the magnetic potential energy of the magnet in the magnetic field. Magnetic potential energy is defined as work done in rotating the magnet from its perpendicular position to some angle in the magnetic field. It means what? That if suppose this is the magnetic field B, and here we have the magnet. This is the magnet. This is now south and this is now north. Then this is at angle, this is now pi by 2. Then this is rotated to some angle. Let this angle is theta. So from pi by 2 to theta. Then whatever the work done is done from pi by 2 to theta, that will be equal to the potential energy. The position when this is perpendicular to the magnetic field is the standard position, because in this the potential energy is minimum or zero. So now this angle is theta. With the direction of the magnetic field. This angle is pi by 2. So the work done, the torque, let me find the torque on the magnet. This torque equal to mv sin theta. Work done in rotating through d theta. This dw is equal to this torque into d theta. Torque equal to mv sin theta d theta. This is equal to dw. The work done in rotating from pi by 2 radian to theta, that is w equal to integration pi by 2 to theta. This is equal to your mv sin theta into d theta. So this work done is called the potential energy. It is called magnetic potential energy. Magnetic potential energy. So this U is equal to W, or this is equal to integration pi by 2 to theta mv sin theta d theta. So now this mv is constant, and this integration pi by 2 to theta, this is now your sin theta d theta. This is mv, and this sin theta equal to minus cos theta. Now this is pi by 2 to theta. So this is mv minus cos theta plus cos pi by 2. And this cos pi by 2 is equal to 0. So we are having this u equal to minus mv cos theta. This is so much. So I told you that when the magnet is perpendicular to the magnetic field, then this is the standard position where the potential energy is, or the capacity of doing work is equal to 0. So that we take the standard position. So this is why we take in definition that this should be rotated from pi by 2, or the perpendicular position of the magnetic field, to the some angle in the magnetic field. So now we can write it in the form of the vector Now we can also express this u is equal to minus m dot b. M dot b. So potential energy is equal to the negative of the scalar product of magnetic moment and the magnetic field. Thus magnetic potential energy is equal to the negative scalar product of magnetic dipole moment and magnetic field intensity. Magnetic field intensity. So now we can understand the stable and unstable position of the magnet. So now we take some specialties. Special cases. First, if theta equal to 0 degree, then this potential energy equal to minus mv cos 0 and u is equal to minus m. This is the minimum potential energy. Minimum potential energy. Minimum potential energy. It means what? That when the magnet is parallel to the magnetic field, this is the most stable condition of the magnet. It is most stable equilibrium of magnet. And also we we can have that when the angle is 0, the torque is equal to 0. So no torque is acting in this position, and the burden is also equal to the MB, that is equal to also 0, because torque is not acting, so this burden will be equal to 0. So no work is required when the magnet is parallel to the magnetic field. So in this one what we have, or this M parallel to B, these are parallel to each other. So this is how to show in this. This is now suppose the magnetic field. This is now suppose magnet. This is magnet. Then S must be here and N must be here, so that the magnetic moment is in this direction. In this condition, this applies, theta equal to 0. Now then, theta equal to pi by 2. Now the second question. If theta equal to pi by 2 radian, then this potential energy U is equal to minus mb cos pi by 2. So U is equal to 0. Means that in this condition the magnet has no ability to do the work against the torque. This is the standard position. It is standard position. The magnet has no ability to do work against torque. So this we take this U equal to 0 in this position. This is why that we are taking the definition to this condition. And now third, if theta equal to pi radian, then this U is equal to minus mb cos pi. Cos pi is equal to minus 1. So this U makes to U, this is now U plus mb. Here the potential energy is maximum. This is the maximum potential energy. Maximum. This is the most unstable equilibrium. It is most unstable equilibrium. Most unstable equilibrium. It means what? That if suppose magnet is placed in this condition, then it will try to come parallel to the magnetic field. So what we have here, this is now equal to pi, or we can have this is now suppose magnetic field B, and magnet is like this one. This is now suppose magnet. This is your N and this is S. Then magnetic moment is in this direction. This is now M. So this M and this B are anti-parallel to each other. Anti-parallel, then the potential energy is maximum. This is most unstable condition. So in this what happens, that this magnet rotates and it tries to come parallel to the magnetic field. In this condition, the magnet has the tendency to rotate itself. Magnet has tendency to come parallel to magnetic field. Parallel to magnetic field. So this is now we can have the comparative study of these two. You can find that in case of pipe, the work done is equal to 2 MV, this is equal to so much, and that work done when this is now 0, then this work done equal to 0. So this is now MV cos theta, u equal to mv cos theta, and work done is equal to mv sin theta. So this is about the potential energy of the magnet. So thank you very much.